Okay, um, video 2, the calculus of parametrics. Um, it was kind of fortuitous that the end of the, like, about 15 minutes hit when we got there, because we do have the graph here, and it tells us where the graph intersects. I was having a moment of self-doubt. I was like, is there a way to algebraically determine the point of intersection if you don't have your calculator? And in this one, it actually winds up being relatively straightforward because you have the benefit of having periodic functions, both being sine, and knowing the periods of both of these functions. You could sort of reason it out relatively easily. I went back and just double checked to make sure, and there is no example that I can find where you are required to find the point of intersection, because that would require kind of a weird system of equations. But so we're just going to go ahead and move forward. And if I run across an example in the coming weeks where you actually are asked without a calculator to find those points of intersection, then we'll deal with that when it comes up. But here we have the point of intersection. The point of intersection is the origin, okay? And I know that sine of 2t winds up being 0, so x winds up being 0, every pi, or every pi over 2, right? Because sine of 2t has a period of pi, and therefore has intersections of basically it returns to 0 every half period, okay? Now, this actually looped this around for 0 to 2 pi. Remember when we went to the window, it was 0 to 2 pi, 6.28. But you actually could, now once you know the point of intersection, wind up doing it rather easily, right? You can say 0 is equal to 2 sine 2t, and 0 is equal to 3 sine t. And therefore 0 is equal to sine of 2t, and therefore 2t is equal to, well, where is sine 0? Well, sine is 0 at 0 pi, so 0 plus pi n. But then, of course, you divide through by 2, and you get 0 plus pi over 2n. Now, over here, it winds up being a little more straightforward because you don't have a coefficient on your angle measurement expression. And that winds up being 0 plus pi n. Now, of course, this one happens more often, so this is going to return to 0 more often than that is, which you can actually see on the graph, right? X returns to 0 here, but y hasn't returned to 0. X returns to 0 here, but y hasn't returned to 0. So X actually returns to a 0 measurement twice as often, which is exactly what we wind up seeing in terms of our analytic work, right? So it's 0 but y isn't, it's 0 and y is. It's 0 but y isn't, it's 0 and y is. So you see how it loops around in that sort of rough figure 8. Okay, so I know that what we're looking for is t is equal to 0 and pi and 2 pi, etc. Okay? But here's the thing. It basically repeats itself after 0 and pi. So what I really want is I really want tangent lines for 0 and pi. Well, let's go ahead and get the derivative. And I know that dy dx is going to be 3 cosine t over 4 cosine 2t, okay? Well, I mean, you can, and you can actually evaluate that at 0 and pi relatively easily, right? Because basically you needed just straight up differentiation for the dy dt, but you needed the chain rule for the dx dt, which is why the 2 turned into a 4 right here as a coefficient. So dy dx at t is equal to 0, and you're going to get 3/4. Dy dx when t is equal to pi, and you're going to get 3 cosine of pi. Well, that's going to be -3. And then you're going to get 4 cosine of 2 pi, so that's going to be +4, okay? And so all you have to do is you just have to do, 0, 0 with 3/4, so y is equal to 3/4 x, and then 0, 0 with a slope of negative 3/4. So those are your two tangent lines, okay? And that kind of makes sense. I mean, if you look at it right there, you do see what looks like, oh, sorry, let's see if I can put that in an area where I don't get the glare back. And you see sort of, you can see how a slope of 3/4 might run right through there, and a slope of negative 3/4 might run right through there, okay? Now, let's go ahead and look at perhaps another example of that. So if we spend a little bit of time on this, we may actually wind up getting to 5 videos instead of 4, but that's just fine. Let's do the same thing. Find the equations of the tangent lines for this at the points of intersection. Now, I already have this plugged into the calculator, so let's go ahead and go here, turn this one off, turn this one on. Now this one is not going to be periodic, so I want to go back to the window, and let's just, doesn't have to deal with pi, but let's just go ahead and do it that way. And boom. Okay, well that kind of looks like 2, 1, okay? Well, let's go ahead and calculate, let's go ahead and calculate a value, okay? And let's, actually, I don't know how to do that calculate in the parametric. Well, let's go ahead and look at 2, 1, okay? So I know if t squared minus t is equal to 2, and t cubed minus 3t minus 1 is equal to 1, right? Because the ordered pair was 2, 1. That's what it looked like on the screen. Well, let's go ahead. Now this one is going to be really, really complicated, but this one's really not. So I have t squared minus t minus 2 is equal to 0. That factors into t minus 2 and t plus 1, and therefore it should be t is equal to negative 1 and 2. Well, it's easy enough to go ahead and plug this in and see whether it's actually true, whether that's true for these values, okay? So I have y of negative 1 gives me negative 1 cubed minus 3 times negative 1 minus 1. That's negative 1 plus 3 minus 1. That is indeed positive 1. Cha-ching. Let's go ahead and try it for 2. That's 2 cubed minus 3 times 2 minus 1. That's 8 minus 6 minus 1, and that is indeed 1. So both of those values work for 2, 1. So really what I'm trying to do is I'm trying to use this point, and I'm going to use these t values through my dy dx in terms of t to find the slope. So I guess now I just need to find dy dx in terms of t. So dy dx is going to be, well, that's going to be 3t squared minus 3 over 2t minus 1. Okay? Now, I need to go ahead and evaluate this at t is equal to negative 1 and 2. So dy dx at t is equal to negative 1 gives me 3, negative 1 squared minus 3 over 2 times negative 1 minus 1. And that's going to give me 0 over negative 3, or 0. Okay, so at t is equal to negative 1, I'm going to have a slope of 0. So that's going to give me y is equal to 1 as a tangent line, right? Because if it's going to be a slope of 0, all I need is the y coordinate from my ordered pair right here. Well, let's go ahead and let's evaluate dy dx at t is equal to 2. And we're going to get 3, 2 squared minus 3, 2 times 2 minus 1. And that's going to be 12 minus 3, which is going to be 9. Okay, it's going to be 4 minus 1, or 3. So I'm going to get a slope of 3. And so I just need to do y minus y1 is equal to m times x minus x1 in order to find the other one. So that's going to be y is equal to 3x minus 6 plus 1, so minus 5. And that should be the other tangent line. Now let's go back to the graph and let's see whether that looks reasonable. Okay. And I think it does, okay? Because remember, it started over here and it looped up like this. Right here at the point of intersection, that looks pretty flat on that initial part of the graph. That could be a slope of 0, so y is equal to 1 looks like a reasonable one. Then it came down and it looped through, and I guess at t is equal to 2, it hit right here. Now that is pretty steep. That looks steep enough to be a slope of 3, and at that trajectory coming down, that would be a y-intercept down there of -5. So those do look reasonable in terms of being in accord with the graph that we got by using our calculator. Okay. I don't want to go ahead and start on area at the tail end of this particular video, so we'll make this video a little bit short, and we'll start on area in the third video. If you have any questions, as always, please do email me. Bye.